Welcome everyone to this second week of this course on radio astronomy. We're very happy to offer this course as the first time in NPTEL. Last week, what we did, we introduced the subject of radio astronomy, uh, informed you about few ongoing projects, future prospects, as well as pre-established radio telescopes and basic science, what is done through radio astronomy. We also introduced you to some basic prerequisites of electromagnetics, have taken you through different derivations, a little bit of pointing vector, pointing flux, introduced again back the Maxwell's equations, and also the polarization of electromagnetic waves. We have also shared a little bit of tutorial which should have helped you with the assignments. They are very normal. This week we have couple of themes in mind. The first one is to introduce you to some important milestones in the history of radio astronomy, how this all came to being, who are the main contributors towards this astonishing field of radio astronomy, and and what are the important telescopes that paved this way in the early stages. So with that, we just proceed. This is again a brief overview of the electromagnetic spectrum. We have shown it in different way earlier. You can see the percentage of transmission and through the atmosphere. So you can see near the radio frequency 3 megahertz to about 30 gigahertz or so, the band is very clean. You can observe it from the ground. But as you go to higher and higher frequencies, things becomes not that easy, and you have to rely on space-based observations. Of course, there is a minor fraction in visible region where you can still observe from the ground, but the troposphere of the Earth atmosphere becomes a bit of a problem. So you typically see very powerful optical telescopes are typically at a very higher altitude. Okay. So with that, we proceed to our current narration. So we have already introduced Maxwell's equation. So James Clerk Maxwell is really the founder of the basic physical theories in electricity and magnetism that defines the platform on base of which the entire radio astronomy stands as of today. We have already discussed Maxwell's equation, so I think the most of the work through Maxwell is already discussed. We know that all the four important Maxwell's equation and the different variants of that for different usage. The next important figure in this discussion will be Heinrich Hertz, who did the first observation of electromagnetic waves. Maxwell did the hard work of all the theoretical derivations, formalism, etc. Heinrich Hertz actually did the first observation. In 1888, he built a system for sending and receiving 5-meter radio waves over short distances. Extremely important to note this. Then Guglielmo Marconi improved the transmitter designs and actually received a Nobel Prize for the first long-distance radio wave communication. And so that was a very powerful discovery. It was made, and the first transmitters, receivers, which actually can do these communications, were discovered initially at the stage by Marconi. He received Nobel Prize for that. However, we have a little bit of different take on that. Closer to home, Professor Acharya Jagadish Chandra Bose was the first person who actually demonstrated way before Marconi did um, the transmission of radio signals for more than 1.5 miles. In 12th December 1901, Marconi used actually Bose's 1899 improved version of the coherer to receive the first transatlantic wireless signal. It's all documented. However, for whatever reason, Marconi received the Nobel Prize, and Bose's contribution now has really come to everybody's acknowledgement, and he's really acknowledged for his initial work. However, the Nobel Prize for the first communication still goes to Marconi. That was the important discoveries and important milestones regarding radio waves and communication, without which the following discussion from henceforth would not be possible. But if you really come to the what was the first epoch, first instance where radio astronomy was essentially born, it was by an accident. We call it serendipity, but it was really an accident. Uh, what happened was this gentleman called Guth Jansky. He was an engineer at Bell Telephone Laboratory, and he was investigating interfering static signals in the wireless communication. So they were built a 20 megahertz directional antenna, and was receiving a static signal which keeps repeating at a sidereal rate. So Jansky was the one who inferred this is not coming from any interference nearby, but it is instead indeed a cosmic signal which has been received from towards Sagittarius, which lies to the center of our Milky Way galaxy. And this really, I mean, they were not supposed to be looking for radio waves coming from cosmic sources. They were doing some experiment to understand some systematics, static signal in their system, and this is what they end up getting. So in 1933, the first detection of radio waves was announced, and Karl Jansky undoubtedly is the father of radio astronomy across the world because of this. He did the observations, which later on his Woodruff Sullivan actually converted them to this contour map, where Jansky observed, and it was a phenomenal discovery. But the takeaway point from there, they were not looking for this extra, cosmic signal. They were looking for something else. But it was essentially an accident or serendipity, whatever you want to call it. This was great. Glad that it happened. So Karl Jansky is really the first radio astronomer in its true sense, that who did it by accident, but then followed up with observations. However, looking at Karl Jansky's work, I mean, the next person, Grot Reber, got very excited, and he actually jumped in as a first radio astronomer. So, if you really want to claim that, and this debate is still out, I mean, Grot Reber is knowingly built a 9-meter parabolic reflector in 1937 in his own backyard, and then observed at 3 different frequencies, conducted the first sky survey at radio frequencies. Truly, the a radio astronomer by hobby or by profession. So that was this is Grot Reber in front of 32-meter and 32-inch feet antenna. Sorry, this is currently lying in the Green Bank Observatory of National NRAO in US. This next slide shows us the contour maps, the strip charts on the top, and the contour map of the galaxy at 160 megahertz. So if I go back, if you go to Jansky's observations in 1932, they were made at 20.5 megahertz. Okay, and unfortunately, Jansky was taken off the project, and it didn't quite materialize after that. And then, but looking at his work, Grot-Reber got excited, and he built a new telescope, and that went on observing at a little bit higher frequency at 160 megahertz. The next person in the list to be mentioned is Joseph Posse. He was developed microwave technology for Australian Navy during World War II, and this in the figure over here is the famous sea interferometer on the Dover Heights, which is near Sydney. It's basically the same concept as Lloyd's mirror, and so you have a direct ray and a reflected ray from the sea surface, and they all come and interfere near the antenna. So this was used as a very powerful technique at those times. The next person to mention is Sir Martin Ryle, who worked on airborne radar during the World War II. Now, World War II is a very important aspect in the development of radio astronomy. Lots of dishes, lots of radars were used for communication purposes. And after the war ended, those were lying just like that for somebody to make use of it. And that, compelled or aided the motivation of the then radio astronomers or engineers for pursuing this kind of cosmic observations at radio wavelengths. So he first published radio interferometric observations. He actually introduced a very critical concept of Earth rotation aperture synthesis to radio astronomy, for which actually he received Nobel Prize in 1974. So he was instrumental in building this multi-element interferometer. This is the 1 mile telescope in Mullard Radio Observatory, and this is the Ryle telescope, or 5-kilometer telescope in Mullard Radio Observatory. So Martin Ryle also is very important in leading the entire 3C survey, which are basically the first, the third Cambridge survey of sources. This became very important catalog of sources, which then people kept on observing on and on and on, and to understand the sources, the properties, the variabilities, etc., etc. We'll come to all of those, but just to note the contribution that this aperture synthesis is extremely important when we come to interferometry. And interferometry is the most novel way to go after, to combine collecting area and resolution at the same time, which we discussed in the first week. But we will definitely come much more in details as the course progresses. So that's the timeline. The next person to be mentioned is Jan Oort. Is a Dutch astronomer and father of Dutch astronomy, very adeptly. He was expert in Milky Way structures. He was instrumental in building Dwingler telescope, 25 meter. It operated 21 centimeter or 1.4 gigahertz. That's towards the left bottom corner of the slide. It was built in 1956. These timelines are very important because, as you see, in 1932-33 was Jansky, then came Grot-Reber, 1937. Then you see for 1946, the first a multi-element interferometer built by Martin Ryle. And then you see this 56 comes the Dunlop telescope in Netherlands. He also built Jan Oort also built the Westerbork array consisting of 14 dishes, 25 meters in diameter, each of them. They operated between 300 megahertz and 8 gigahertz. It was done in 1970s. So, but unlike the VLA, the first, I showed you the picture in the very first um, week, um, and also GMRT, it is not a 2D array. It's along one-dimensional linear array, and have some limitation, but we can discuss it later on. Also, Janot was very crucial in has a crucial role in detection of H1 21 centimeter line emission from the Milky Way. Although it was done actually by Van der Hulst in 1944, but he played a very important role, which we can discuss when we come to that towards the end of this course. We come next to a person who is Professor Govind Swarup, who is the father of radio astronomy in India, and he indeed done a remarkable job of building 3 telescopes. The first one was built in Kalyan Radio Telescope. It was built at 610 megahertz, 24 dishes of 1.8 meter diameter each. It was done in 1965. Then he built a UT Radio Telescope at 326.5 megahertz, a cylindrical parabolic dish. This is towards the left-right corner. You can see this. We'll show you more pictures throughout the course. It's in Ooty. It was built in 1970. So 65, he built Kalyan Telescope. Then he, from some old dishes from somewhere else. We'll come to that story later. In 1970, he built Ooty telescope, which is cylindrical parabolic antenna, quite different in design than all the other dishes we have seen so far, but has very, very good relevance to some of the telescopes which are currently operational in Canada and elsewhere. So in 1970, he built an Ooty telescope at a different frequency, 326.5 megahertz. And then finally, in 1997, the giant meter wave radio telescope operating below 1.6 gigahertz was actually finished construction. It started earlier. It's 30 parabolic dishes. We discussed it last time, with 45-meter diameter, each of them. So it's truly a remarkable man, a remarkable contribution, and for Indian radio astronomy, he was really the father. A few other major discoveries in radio astronomy to note: pulsar, the rotating star, was discovered in radio. There are lots of other, don't get confused, lots of other discoveries in astronomy. We are focusing here only the ones which were discovered in radio wavelengths. Okay, so that's how this thing is done, not in particular order. Pulsar is the rotating star, a phenomenal object to study. It is so the pulse periods are so constant that it is sometimes often used even for navigation purposes. Jocelyn Bell and Tony Hewish was discovered in pulsar, although only Tony Hewish got the credit and got the Nobel Prize. Jocelyn Bell didn't. That's a separate story. Next is cosmic microwave background, was discovered by Arno Penzias and Robert Wilson. Extremely important discovery, particularly to understand how the universe was formed, how it is evolving. Before that, there were several theories, but this kind of cosmic microwave background kind of sealed it that there was a Big Bang and then what followed. So more on CMB later. Then quasars were discovered late 1950s by Martin Ryle et al. And his group. Radio galaxies were discovered by Grotriber, Bolton, Stanley, 1940 to 1950s. These are very, very phenomenal discoveries. Radio galaxies, quasars, CMB, pulsar, etc. Now, a few important contributions, Nobel Prizes. As I said, Martin Ryle, Tony Hewish, they received Nobel Prize in radio astronomy. Then 1978, Penzias Wilson, they received Nobel Prize also for the discovery of the cosmic microwave background. Different types of pulsar was discovered, and a important probe to study gravitation. And for that, Russell Hulse and Joe Taylor received Nobel Prize in 1993. Later, the first important although Penzias and Wilson discovered it, the CMB, but they didn't went into details about understanding structures in the CMB and this dipole nature, the anisotropy in the CMB radiation. That was done by John Mather and George Smoot using the Kobe satellite and also the help of WMAP. And for that, they were awarded Nobel Prize in 2006. So with this, we are coming close to, there are many other discoveries, many other telescopes to be mentioned. This is not an exhaustive list. This is just initial, kind of instigation to understand a lot of important works have laid to us what we hear and why this course is relevant. So this is not a new course or a new material. So I have referred to a lot of other existing slides and books for gathering this. So there's some references. I will also put up an exhaustive list at some point in the future slides, future lectures. Sorry. So glad if you have enjoyed it and look forward to seeing you to the next lecture. Thank you.